Good afternoon, friends. Welcome to this third and final session on balancing of rotating and reciprocating machines. We have talked mostly about rotating machines. We have introduced the kinematics of the slider crank mechanism. The reciprocating machine that we were mostly concentrating on is that of an IC engine mechanism, which is an example of a slider crank mechanism. So, in the last class, to refresh your memory, among other things, in the last part of the last class, I should say, we had talked about the kinematics of this slider crank mechanism. It was shown to you how the exact kinematic analysis can be performed. So, these are the results, if you remember, for the exact kinematic analysis, but then we were also able to do an approximate kinematic analysis, and the basic premise of the approximate kinematic analysis was that you define a variable which is called lambda, which is nothing but crank radius divided by connecting rod length, and this, in practical situations, this value lambda turns out to be very small, of the order of 1 by 3 or 1 by 4, and therefore whenever we see lambda, we can invoke this assumption that lambda is small, and then as a result we get a binomial expansion possible, and in this binomial expansion we choose to keep only terms of the order of lambda square in this first expansion, and then we will get the kinematics appropriately reduced. So, here we see therefore that all the kinematic quantities, namely position, velocity and acceleration, are given in terms of two trigonometric functions, namely cos theta cos 2 theta or sin theta sin 2 theta, and these are called first order and second order. There will be more orders depending whether you wish to take a more accurate solution, but usually for this solution is fairly accurate, and to demonstrate the accuracy of the solution, I have plotted in this slide the comparison between the exact analysis without any approximation in blue, and in red dots I have plotted the approximate analysis for a lambda value which is equals to 1 by 3. As is borne out through this result, the exact and approximate analysis is fairly giving us the same results. So, today we will adopt the inverse kinematics approach. In the last class we had just introduced this idea. So, in the inverse kinematics approach, you will recall what we have is that the position, velocity, acceleration of this entire mechanism has been determined. So, what we are saying is that the crank speed is uniform, the crank is rotating at a uniform angular velocity omega, and once you have that, we have by now means to find out the position, velocity, acceleration of the piston or of any other point. So, position, velocity, acceleration of any point of the mechanism is known once you say that the kinematics of the crank is that of uniform angular motion. So, now we move on to the dynamics of it, and for this for the study of dynamics, the inertial properties will be very essential, and by inertial properties what we mean is that the mass, the center of mass location and the moment of inertia. So, for every geometry till now while doing kinematics we were not bothered about the exact geometry of the parts of our engine, but now we will need to know some details about the geometry. The details which will be required are the following: mass, the center of mass location and the moment of inertia about center of mass. And today to start with, what we are going to do is the following: we are going to formulate the equations of motion for each part, and the main challenge in that factor is that we are going to account for not only the applied forces but also the reaction forces which come from the joint. That will be clear to you in a moment. And as a result of this analysis, we will be able to determine the applied force which ensures the desired kinematics. Remember, the kinematics that we want is that of uniform angular motion of the crank. To get this uniform angular motion of the crank, we require to apply certain kind of forces. So, through this analysis, we will be able to determine what forces or moments will produce this kinds of motion. To be specific, we will look at the moment that is to be applied at the crank radius at the crank such that we get uniform angular motion of this crank. So, this is the inverse kinematics approach. Please understand, this approach is in contrast with the forward dynamic approach. In the forward dynamic approach, as you would have learnt in your engineering mechanics class, there you would have given a forces, and given the forces you try to find acceleration. From the acceleration you integrate it to find the velocities, from the velocities you integrate it once more to find the position. But in the inverse kinematics approach, you you first fix the kinematics and then determine the forces which will cause this kinematics. So this is the inverse kinematics approach which will be taught through this lecture. There is also the forward dynamics approach which is possible, that will be known to you in case you take a course in multi-body dynamics, but in this case we are going to limit ourselves on the inverse kinematics approach. Okay, so with that refreshing of our memory, let us now turn to the lecture material today. So here what you see in this slide is the free body diagram of each and every part of your slider crank mechanism or the IC engine mechanism. So here in purple what is shown is the crank, in red we have shown the connecting rod, and the blue blocks over here is the piston. So each of these parts are now detached, and now we are going to draw the free body diagram of each of these parts. So as I said, on the crank we are going to apply some moment, I am sorry, this blue curved arrow denotes some moment. So this is an unknown applied moment on the crank such that the crank moves at a constant angular speed. There is another force which is applicable here. On the piston side you will have the gas force, but the gas force is known from thermodynamic considerations. Let us say the gas force is known. The unknown applied force is the moment, unknown applied moment is the torque which is applied on the crank. So if there is an moment which is equal to value of m, that moment should be such that the crank rotates at the constant angular speed. So there is one unknown applied moment to start with, but all the reactions at all the joints are also unknown. So for example, you will remember that the crank is connected to the frame at a revolute joint. So if I draw the free body diagram of the crank alone, then I should account for the interaction forces between the crank and the frame, that I am calling it as R12. So R12 comma x is the force from the member 1 to the member 2 in the direction of x. Similarly, R12 comma y is the action reaction force, is the force that is given by the member 1, which is the frame, to the member 2, which is the crank, along the direction y. So with that nomenclature, the free body diagram of the crank, let us say, will have an unknown moment over here. There are unknown forces which come from the interconnection with the crank. I call them R12 comma x and R12 comma y. And similarly at this end where the crank is connected to the connecting rod, because of the interaction forces between the crank and the connecting rod, there are forces at play. So R32 comma x denotes the force from 3 to 2, that is, if you recall, 3 is our connecting rod, 2 is our crank. So R32 comma x denotes the force from the connecting rod to the crank along the direction of x. Similarly, R32 comma y denotes the force from the member 3, which is connecting rod, to the crank along the direction of y. Okay. To exemplify another, to give you another example, let us now look at this piston. On the piston you have a gas force which is known, as I said, from thermodynamic considerations. The piston itself is bearing the an action reaction force which is coming firstly from the connecting rod. So the connecting rod which is connected to the piston will give a force, the connecting rod will give a force to the piston, which is symbolized as R3 comma 34 comma x in the x direction and R34 comma y in the y direction. So R34 denotes the force from 3, which is the connecting rod, to 4, which is the piston. And when I say comma x, I mean it is along the direction of x. Similarly, comma y means along the direction of y. And also this piston block will get to see a force which is R14. R14 by the seminal nomenclature is the force which the frame offers to the piston. The piston, due to its interaction with the frame, is going to get a force R14 comma y. At this stage we are assuming that it is having a frictionless contact with the frame, that is there is no friction between the piston and the frame. So that is obviously a simplistic viewpoint, not true in reality, but to keep ourselves within the limits of complication we are assuming that to be true. but you can include a friction force in a more advanced calculation that will give you one more force, but at this stage we wish to keep that out of the discussion. So at this stage we say that the force which the frame gives to the piston is only along the direction y, and we symbolize this as R14, y. There is no x directional force because we are saying that the piston is moving within the inner walls of the cylinder without any friction. So that were the forces on the piston. Now coming to connecting rod. On the connecting rod, because on the connecting rod on the side of the crank, because the crank was getting a force R32, the connecting rod will get an action reaction pair of this force. So the force that is acting on the connecting rod from the crank side will be just equal and opposite to these R32 forces. Remember, R32 was defined as the force from the connecting rod to the crank. So therefore, as a reaction to that force, the connecting rod will receive an equal and opposite force. These are indicated by these arrows. So the action reaction pair to this force is given by this, which is acting on the connecting rod. Similarly, the connecting rod was giving a force R34, x and R34, y to the piston. Because of the action reaction principle, it has to get back equal and opposite forces. So therefore, instead of R34, x, now the force which comes and hits the connecting rod is R34, x in magnitude, but it is opposite in direction. So these forces are the action reaction pair of these forces, and therefore these forces are the forces which are coming from the piston to the connecting rod. Okay. So therefore these are the forces which are there. These are the reaction forces which are there due to all the interconnection. So if we just count how many forces are such reaction forces are there, we see that there are two forces here, there are two forces here, there are two forces here, there is one force here. So there are 7 reaction force, 2 plus 2 plus 2 plus 1. So that is 7 reaction force. I don't count the forces on the connecting rod because that would be double counting. If I know what are the forces coming on the crank from the connecting rod, I can evaluate what are the forces the connecting rod receives from the crank, because that is well known, that is just an action reaction pair. So I don't count these reaction forces as unknown, because once I determine these forces, I should be able to determine the reaction to those forces. So therefore there are 7 unknown reaction forces which are happening at the pin joints and also on this sliding pair, and there is one unknown applied moment which is shown by this curved arrow M. So therefore in totality there are 8 unknowns in this system. Let us see if we can find out 8 equations such that we are able to solve this system of equation. So now we will look part by part. So this was the free body diagram of each part shown together. Now we will look at the free body diagram of the crank in isolation. So this is the free body diagram of the crank in isolation. The center of mass is indicated by this black dot. So this is the center of mass of the crank. So it is at a distance d2 and from one end and f2 from the other end. Now mass times acceleration in the x direction should be equals to the sum total of all forces in the x direction. So the forces on this crank in the x direction is R12, x and R32, x. So therefore you have m2 times a2 in the x direction. A2 is the acceleration of the center of mass. So acceleration of the center of mass in the x direction multiplied by the mass of the crank should be equal to the sum total of the forces along the x direction, which is R12, x and R32, x, right. Similarly, mass times acceleration along the y direction should be R12 in the direction of y plus R32 in the direction of y. And lastly, about the moment equilibrium. So I2 is the polar moment of inertia about the center of mass of this object, of this crank. So I2 times alpha 2. Remember, we have already assumed that we are interested in the situation where the crank is rotating at a constant angular speed. So therefore the angular acceleration of the crank is 0. So I2 alpha 2 should be 0, which means the sum total of all moments acting on the crank should give us a 0. So what are the moments? The first one is the applied moment, The second one is the moment due to this force R12 comma x. So R12 comma x will have a moment arm about the center of mass given by d2 sine theta. So d2 sine theta is the momentum which is perpendicular to the force. So R12 comma x into d2 sine theta is the moment. Please note the moment created by this R12 comma x is exactly in the direction of m. The direction of m has been taken as counterclockwise. So R12 comma x about this point is also creating a counterclockwise moment. But R12 comma y is going to create a clockwise moment, therefore it is coming with the negative sign, and the moment arm corresponding to this force R12 comma y is d2 cos theta. So there is a d2 length, and if you take the cos theta component of it, that forms the moment arm about the center of mass of this force R12 comma y. So therefore you have a minus R12 comma y d2 cos theta as this term. You will also have a moment due to R32x, and this time this R32x is going to create a clockwise moment about the center of mass. So therefore it comes with a negative sign, and the moment arm corresponding to it will be F2 sine theta. This is F2, this angle is sine theta, this angle is theta, so therefore this is F2 sine theta. And similarly R32 comma y is going to create a counterclockwise moment like m, and therefore R32 comma y comes with a positive sign, and the moment arm corresponding to this will be exactly F2 cos theta. So this is a set of three equations which are basically the equilibrium conditions for our crank. So we have three equations of motion for the crank at this stage. Remember, we have 8 unknowns which we have to determine. From the crank itself we have got three equations. Now let us look at the connecting rod. So just in a similar fashion we draw the free body diagram only of the connecting rod. So again, mass times acceleration of the connecting rod in the x direction should be equal to the sum of all forces in the x direction. This time there are two forces in the x direction, R34 comma x and R32 comma x. So these two forces come with a negative sign, and that should be equal to M3A3 comma x. Similarly M3A3 comma y, mass times acceleration of the center of mass along the y direction should be the sum total of all the forces along the y direction. So that is R34y and R32y, but both have directions opposite to the y direction that we have chosen. So this comes with a negative sign. And lastly we have to account for the moment balance. So I3 is again the moment of inertia about the center of mass. Alpha 3 is the angular acceleration of this connecting rod. This time it is chosen in this fashion. So therefore R34 comma x is going to create a positive a moment which is along this direction. So this is going to create a clockwise moment because the direction of phi is as indicated in this diagram. So I3 alpha 3 is clockwise positive, alpha 2 was counterclockwise, but this is clockwise. So therefore the moment arm corresponding to R34x is going to be F3 sine phi. So F3 sine phi is this distance, F3 sine phi multiplied by R34 comma x is the moment which is created because of the force R34 comma x. So that gives the moment which is along the same direction as phi, and therefore it comes with a positive sign. Same thing happens for R34 comma y, it comes with a positive because R34 comma y is going to create again a clockwise moment. This is going to create a clockwise moment, and therefore this is positive. But the moment arm this time is got to be F3 cos phi. Okay, so therefore these two terms are settled. For the moments created because of these forces are going to create a counterclockwise moment about this point, and therefore they come with a negative sign, and it is easy to find out that the moment arm corresponding to R32 comma y is d3 cos phi and R32x is d3 sin phi. So therefore these are the moment arms, and therefore we should be able to write down these equations. So again we have obtained for connecting rod three equations were obtained for the crank, 3 equations are now obtained for the connecting rod. So 6 equations is made available to us at this stage. Finally, the equation of motion of the piston is as follows. Now in the piston there are 4 forces R14 which is coming from the frame to the piston, and because of our assumption that The sliding pair is completely frictionless, therefore there is only one force which is directed along the y direction. There is no x directional forces in the present analysis. And also we are taking that R34x and R34y all are passing through the center of mass, and the gas force is also passing through the center of mass. So there is absolutely no issue about moment balance, because all of these forces are passing through the same point, which is the center of mass. So therefore we will appeal only to the force equilibrium, and that gives us M4A4x is equals to R34x minus P theta A. P theta is the unknown gas force. P is a function of theta because gas pressure is a function of crank angle, that will come out through your thermodynamic calculation. So in general, gas force is not constant, but it is going to change with the crank orientation, and usually in your IC engines course you will get to see different values, different nature of these P theta kind of curves. So as I said, these can be determined from thermodynamic arguments. So let us say this has been done. So P theta is known. Therefore, the entire mass times acceleration in the x direction of the piston is going to be given by R34x minus P theta times A. And similarly, M3 times A3y, but then this is a piston which is sliding only along the x direction. If it is sliding along the x direction, there is no acceleration in the y direction. So M3 times A3y should be 0, which means R1 4 comma y, which is, again to repeat myself, which is the force that the frame gives to the piston, that plus R3 4 comma y, which it gets from the connecting rod, that together should give us a 0. So these are the two equations of motion for the slider. We already had 3 equations from the crank, 3 equations for the connecting rod. Thus for the 3 moving parts of the body, that is the crank, the connecting rod and the piston, in totality we have got 8 equations, and we had already counted the number of variables as 8. So therefore we have an 8 by 8 system. We can put all of these equations in a nice matrix form. Remember, right in the first slide, as it was shown to you, the unknowns were these reaction forces and this moment. So all these equations, what I have done in slide number 38 is that I have grouped them together such that the variables appear in a vector form, and all the coefficients associated with each of these variables I have put them as matrices. So each row of this matrix is going to actually indicate one of the equations which has been derived in one of our previous slides. And since the kinematics is known in the inverse kinematics approach, as we have argued, the kinematics is known, and with that premise we are trying to evaluate the unknown moment as well as the reaction forces which are coming at the different joints, and therefore these can be now evaluated, because the right hand side is only going to depend upon the inertial properties, that is the mass and the moment of inertia and the kinematics. So the inertia and kinematics both are known. All these parameters are known because these are sin theta, cos theta, sin phi, cos phi, whatever these are, and these d2, f2, these are all geometric parameters which are known. So this is like solving Ax equals to B kind of a system, where A is an 8 by 8 system and B is, the vector B is containing 8 components of a vector. So if you know how to handle such a system, you should be able to solve it. But again, as I say, there is no point in trying to solve this equation in pen and paper. Please don't try to do that. You will unnecessarily make some manual mistakes. Rather, at this stage what you should do, you should take this system on a computer in a scientific computation software and try and solve it. Okay. So again, those of you who keep looking for different projects at different places, take this as a project where you should be able to write this matrix equation, put it in a computer and just solve it for different values of, let us say, the p theta. For different engines you will have different p theta, for different values of theta also you should be able to solve it. So this is in effect, now the equations have been formulated, but you should not attempt to solve this equation because this is too big for a manual pen and paper solution. You should take it on a computer and get it solved. But at this stage I will try to convince you that the formulation of these equations of motion has been attained, and the formulation, please try and understand, and I emphasize this point again and again, that it is just a simple application of Newton's laws of motion, something that you have learnt in your first semester of engineering mechanics course, probably even in your high school physics, but you have to apply all these Newton's laws of motion in setting up these equations of motion. Fine, these equations of motions will be long and complicated. You will just be able to write it in a big sheet of paper, but don't try to solve it. Doesn't matter if you cannot try to solve it in pen and paper, solve it in computer, and you should be able to get very useful output. The output of this solution is specifically this value m, which is the applied moment which will ensure that our crank rotates at a constant speed, and also all these reaction forces. So this is what I wish to discuss, that for the desired kinematics at this stage, if the solution is, let us say, obtainable from a computer, after once the solution is obtained, we will be able to find out what is the required torque such that the kinematics of the crank is that of uniform angular motion. The torque, this torque which is applied to the sorry, this is not going to be connecting rod, this is going to be crank. The torque which is applied to the crank is going to be the load torque. Please make this correction in your notes. This is not connecting rod, this is crank. Torque applied to the crank is going to be called as the load torque. So this is what the engine is seeing in terms, if you have seen a dynamometer setting. So the engine crank is basically going to rotate the drum of your dynamometer. So the dynamometer drum corresponds to certain load torque. So the torque applied to this crank, which in our notation is this m. So this is basically what is the load torque. So the load torque is therefore found through this calculation. Turning moments can also be found, but the turning moment calculation, I will come to it in a moment. More importantly, all the reactions between interconnected members can be found, and remember, this calculation is valid for one value of theta. You have to repeat this calculation in a loop for different values of theta, because this matrix you have entries which will depend on theta, and for each theta the acceleration of the crank and the connecting rod will change, and so will be the angular acceleration of the connecting rod. So therefore this equation of motion is valid for each theta. As time changes, theta changes, the coefficients of this matrix will change, the coefficient of the right hand side vector will change, and therefore the solution vector will also change. So therefore the reaction forces as well as the m, which is the load torque, will be time varying, and therefore once the reaction forces is time varying, again you will get to see that you are inducing fatigue loading in your members, something which we have to be very careful about. So the members have to be so designed such that you can endure this fatigue, the members can endure the fatigue load. So therefore at this point, again to recapitulate, we have been able to calculate the load torque, which was m, and all these reaction forces. But then if the crank is moving at constant speed, the load torque has got to be equal to the turning moment. Turning moment is the moment which is making the crank move because of the gas forces. So turning moment is that moment which is coming because of the gas forces and the inertia forces, and the load torque is that which is resisting that force. So because the crank is moving at a constant angular speed, there has to be a balance between this moment, which is moment m, or the load torque which is applied to the crank, and all other moments due to all other forces, and this all other moments due to all other force is basically the turning moment. So if I look at the free body diagram of the crank, which I will bring up again in a moment. So this is the free body diagram of the crank. This blue arrow is the load torque m, which we have found. All these forces taken together is rather these two forces taken together will form a turning moment, right? And this turning moment and this moment has to balance such that the crank is rotating at a constant angular speed about this point, and this is what we will try and achieve through our flywheel. But before moving to flywheels, I will pause for a moment to find out if there are any questions at this point. What I expect is that you should be able to appeal to Newton's laws of motion and be able to find out what is the equation of motion of the entire mechanism, right? The entire mechanism will involve a lot of variables. In this case it was 3, but a simple routine application of Newton's laws of motion at for each member will enable you to determine all these 8 equations, and when you solve these 8 equations in a computational environment, you should be able to find out everything about this mechanism in terms of its forces. So this is what I wish to convince you at this stage. There are a lot of other things that I have to tell you as we go along in today's class, but at this stage I hope this procedure of calculating or formulating the problem should be clear at this point. If not, please pose your question and interact with me such that I can help you understand this matter. So I will pause for about a few minutes for your question. PSGCT is asking me 3D force analysis is not done. Why? That is because this is a planar mechanism. This is not a 3D spatial mechanism. That is why we do not do a 3D analysis. The frame of in the coordinate system of analysis, if you look at the mechanism, it is just 2D. There is nothing 3D about this mechanism. So there is nothing extra you will get in doing an analysis for the forces in the Z direction, because everything is moving only in the XY plane. There is nothing happening in the Z direction. We are talking about a single cylinder engine. In this single cylinder engine is a planar mechanism. There is no need for doing a spatial analysis for this planar mechanism. Okay, one question. PSGCT is asking me, can you explain the sign conventions in finding moments? For the crank, the sign convention is, when I am writing the moment equations for the crank, it is counterclockwise it is positive, clockwise is negative, but then for the connecting rod, clockwise is positive, counterclockwise is negative. Okay, so it does not matter if you take even you could take even a counterclockwise positive here, that is also possible, but the reason why we are having this discrepancy between the crank and the connecting rod is because our kinematic variable, if you look at it carefully, the kinematic variable is theta in this direction, whereas it is phi in this direction. So if you want your dynamics to be commensurate with the kinematics, then you should have it in this fashion, else you have to take the kinematic variable in this way in case you wish to make your dynamics have a consistent moment between members. But I would prefer it this way, where the kinematics comes first, the kinematics decides your signs. So here the kinematics tells me that the angular position which describes the connecting rod is phi, where phi is clockwise in this fashion. So I will choose the moment to be positive in the clockwise direction for the connecting rod. Similarly, for the crank, it is the kinematic variable is theta, which is counterclockwise. So I will choose the counterclockwise moment to be positive. I hope that clarifies the point. Another question is there, how can crank have constant velocity when reaction forces are time varying? PSGCT is asking me, how can crank have constant velocity, but that is exactly what we want, right? We want our engine to have a crank which is having a constant angular velocity. So we are discussing the analysis when our engine speed is constant. We are not discussing in this talk what is happening when the engine is accelerating. We are now discussing the situation where the engine is having a constant angular speed. So in order to have a constant angular speed, obviously you must put a certain amount of torque. So you are right in saying that the reaction forces are varying in time. The reaction forces here are varying in time, but let us say this moment could also vary in time such that the total moment is 0, and that is exactly what we are trying to enforce through this condition. So if you look at this equation, all the moments taken together is 0. So we are trying to ensure through the application of this moment m, which we are calling it as load torque, this should be constant, this total summation should give us 0. So find R12, R1, R32, all of them could vary, but then the moment could also vary, and together you will have equilibrium. So with the variation of the load torque, this is achievable. More importantly, this is what we want. So we want an m such that you have alpha 2 to be equal to 0. So therefore this load torque is what ensures that despite time varying reactions, you will have a totality of all moment to be equal to 0. I hope that answers your question. Okay, SSETN also has a similar question about the connecting rod. So connecting rod, this is a free body diagram. In the free body diagram, we are trying to evaluate all the moments which are all the moments about the center of mass. So we are not evaluating about the hinged point, we are evaluating the moments about the center of mass. So I3 times alpha 3, I3 is the moment of inertia about the center of mass, not about any hinge point. Okay. So therefore F3 sin phi and D3 sin phi, these are momentums about this black dot which is the center of mass. So I hope that clarifies SSC question, that it is moments which are not about hinge point but about center of mass. So as we said that it is the balance between the load torque and the turning moment. Turning moment is the moment due to all other reaction forces that is appearing in the connecting rod. So in the crank, I am sorry. So typically how what we know is that the load torque is going to be constant, but the turning moment is going to fluctuate because the gas forces fluctuate, the reaction forces fluctuate, the inertia forces fluctuate. So obviously this condition is not true that the turning moment and the load torque is constant, because if your crank has to move at a constant speed, then the turning moment and the load torque has to be equal, but then load torque cannot be fluctuating so rapidly as the turning moment does. So in reality we will have the turning moment and load torque characteristics to be somewhat in this way, where we get to see that the average of the turning moment is going to be equal to the constant load torque, and hence between cycle to cycle there is no change in the angular velocity. The angular velocity across the cycles will remain same, but within the cycle, because the fluctuating turning moment is not able to match up with the constant load torque, within the cycle this balance is not maintained in reality. However, we do not feel an appreciable fluctuation of this speed despite the turning moment not balancing the load torque, because our analysis tells us unless the turning moment balances the load torque, there will be fluctuation in speed. True, there will be fluctuation in speed, but if the load torque balances in an average sense with the fluctuating turning moment, then across the cycle the average angular velocity will not change. That is what is happening. Now if you ask me within the cycle can it change? Yes, it should change, but then it is made minimal. This change is made minimal by the action of the flywheel. So within a cycle we see that the load torque and the turning turning moment is not balancing, which means that within a cycle the crank speed actually fluctuates. It is not true that the crank speed is held constant within a cycle. It is across the two cycles, across different cycles, that the average crank speed is going to be constant, but within a cycle the crank speed does fluctuate, but we are unable to detect that because the flywheel is doing its job, and this speed fluctuation, the crank speed fluctuation, will be minimized by the connection of a large inertia, which is basically your flywheel. So a good flywheel design will ensure that not only the average speed remains constant, but also the fluctuations in speed within a cycle is to a bare minimum. So flywheel design can be done from this premise. Unfortunately we are running too much out of time, so I will leave this flywheel design for you as a self study. It is not a big deal. If you please go through this one slide and you read the appropriate material, you should be able to find it. I will rather spend more time on the unbalanced forces in a single cylinder engine and also come back to multi-cylinder engines in due course. Okay. So now let us see at this stage what we have achieved. So at this stage we have, so if you look at the upper part of this diagram, the upper part of this diagram is exactly the free body diagram of all the moving parts of the machine, namely the purple color indicates crank, the red color indicates connecting rod, and the blue blocks indicates the piston. So we have found out all these forces and all the moments through our previous analysis, hopefully through a computational program. But now if we look at the frame, this is the frame, right? The thick black line is the frame which we had omitted from our previous discussion. Now if R12 is the force from frame, which is link number 1, to the crank, which is link number 2, then there must be an equal and opposite reaction force from the crank to the frame. So therefore there is an equal and opposite reaction force that we are seeing from the crank to the frame. We have already evaluated the forces from the frame to the crank. Now we appeal to Newton's third law of motion, and that tells us that there is an equal and opposite reaction force to this force which is hitting the frame at the joint where the crank and the frame is connected. So therefore, at this point it will see the frame will see the forces R12 and comma y and R12 comma x. Similarly, there is a moment which is given by the external system to the crank. Now that external system is nothing but the frame. So therefore, if M is the moment that is offered by the external system to the crank, therefore there is an equal and opposite moment which is hitting the frame back, because that is a action reaction pair. So therefore, the frame will get back this external moment. Similarly, on the end of the piston, you will see that since R14 comma y is the force that the frame gave to the piston, it will take back a force R14 comma y but with an opposite direction, and it will also take back the gas force, because gas force is hitting on one side the piston and on the other side it is hitting the crankcase. So it will get back the forces. So you remember our final objective was what is the total forces and total moments acting on the frame. This is what we have achieved. We are now saying that the sum total of all forces and all moments that are acting on the frame. We have already found these quantities R12 comma y, R12 comma x, R14 comma y, P theta is anyway known, M is found. All of these quantities are found. So therefore, we can add up the quantities and this will give us the entirety of all the shaking forces and all the shaking moments that is acting on our frame. And remember, our objective will be to try and minimize it through a better design. So at this stage, I wish to indicate to you we have already attained our objective in the setup that we are living in, namely there is frictionless contact between the piston and the frame, and also we have taken a good flywheel which ensures that the crank is running at a constant speed, and all these conditions have enabled us to determine the set of equations of motion which can be solved possibly in a computer, and with that all our forces are determined, and therefore at this stage we are having a very happy situation where all the forces are known, all the forces acting on the frame are known, and they are by definition the unbalanced forces which are acting on the frame. So that completes our analysis in this part of the session, but we will take a deeper dive now in trying to understand the unbalanced forces and unbalanced moments in a completely different perspective, and in fact in that fashion we will be able to recover a simple formula in calculating the unbalanced forces. Please remember, at this stage we have found out the entire unbalanced force. We have not found a formula for it, but we have effectively found out the value of the unbalanced force, because all these forces are found out. We simply have to add it up and that's it, we are done. That is the total forces in x, y direction and also theta direction. So it will be shown to you in a minute that actually there are no unbalanced force in the y direction, there is only unbalanced force in the x direction, which is in the slider direction. So that is not observed in this analysis unless you actually plot out the solution. So in the next analysis we will be able to offer you that insight. So in the next analysis, let us say that this boxed diagram, this box represents a machine. We do not need to worry what is the exact details of the machine. It contains different moving parts and I have labeled them in different colors, a circle, a red triangle, a green rhombus and whatever. So these are all the moving parts on this machine. So let us take something like a control volume approach, and this dotted box is our system of interest, or rather a control system I should say. So this is the control system that we are interested in. So the force that is applied on this control system must be equal to the rate of change of linear momentum. That is again something that we have learned right from our school days. We have revised it thoroughly in our curriculum of engineering mechanics, but here we will appeal to that very simple logic that the force applied on this box, which is the control system box, the box in itself, within itself could contain a number of moving parts, that is beside the point, but the force, total force that is applied must be equals to the rate of change of total linear momentum for all the constants. Okay. So which means the rate of the force should be equal to m1 x1 double dot plus m2 x2 double dot plus m3 x3 double dot. The total force should be equal to m1 x1 double dot plus M2 x2 double dot plus M3 x3 double dot, all of them are moving. So therefore the unbalanced force, this force is coming from the external system, which is the non-moving part, and the non-moving part of the machine by definition is its frame. So therefore this force F, which is coming to the moving parts of the machine, is offered by the frame of the machine onto the moving parts. Therefore the unbalanced force, which by definition is the force which hits the non-moving part or the static part of the frame of the machine, is going to be minus F. So minus F, therefore F we already know is M1 x1 double dot plus M2 x2 double dot plus M3 x3 double dot. So therefore M1 x1 double dot plus minus of F would therefore be minus of M1 x1 double dot minus of M2 x2 double dot minus of M3 x3 double dot. So the unbalanced force which is hitting the frame is basically the sum total of all inertia forces of all the moving parts. So all the inertia forces, if you note, M1 x1 double dot is the inertia force corresponding to the part 1, M2 x2 double dot with a minus sign is the inertia force corresponding to the moving part, which is represented by the red triangle, and so on and so forth. No matter how many parts this machine contains, the total unbalanced force which hits the frame is going to be the total inertia forces of all these moving parts taken together. And this is a very interesting observation, because this will actually permit us to find a very simple formula for the unbalanced force which is hitting our frame in the case of an IC engine mechanism. So the applied moment similarly is the rate of change of angular momentum. So whatever moment is applied in this box is the rate of change of angular momentum. So similarly the unbalanced moment, which is going to be the action reaction pair. So this moment is applied by the part which is outside the moving parts, right. So this moment is applied by the external system onto the moving parts of the system. Now therefore as a reaction to it, you will have equal and opposite to M, which will hit back at the frame. So therefore if M is the force which is applied by the external environment onto the system comprising of moving parts, therefore you get an equal and opposite M, which will be applied by the moving parts onto the static part of the machine or the frame. Therefore unbalanced moment which is hitting the frame is just like unbalanced force is equal to total inertia force of the moving part. Unbalanced moment is the total inertia torque of all the moving members. So this is a very interesting observation, as I said, and we will use this observation to good effect in determining our unbalanced forces in our system. So unbalanced forces, as we know, which if it is permitted to act on the frame, will induce vibration, and therefore we should contain it, something that we have already exposed to you in the opening lecture. So now we have finished the exact calculations as we had seen, but as we had seen that exact calculations has left us with an 8 by 8 system, and there was no compact simple formula which was possible with that 8 by 8 system, and therefore we were able to finally solve our problem and determine what are the reaction forces and what are the shaking forces, but that did not give us a nice compact representation or a formula for it. Now therefore using this concept that the unbalanced forces which are hitting the frame is basically the total inertia force of the moving part, and similarly the unbalanced force which is acting, unbalanced moment is the total inertia torque acting of all the moving members. With this representation we will make an approximate dynamics, approximate not because we are appealing to this unbalanced force being equal to inertia force, that there is no approximation involved there, but we will try and approximate the dynamics or rather the kinematics also of the moving members, and thereby we will attain a very simple representation, a very simple formula which will be very accurate for industrial applications. So here is our starting point. So we are now trying to determine the approximate dynamics for a single cylinder IC engine. The exact equations for dynamics is too complicated to develop an insight into the turning moment and the unbalanced forces. The equations can be formulated, it is a big set of equations. With that big set of equations we are unable to fathom how exactly the unbalanced forces behaved. Is it harmonic? Is it having a simple formula? On what factors does it depend? These questions are not very easy to understand if we look at that 8 by 8 system. Though the solution is possible, the graph of it can be drawn, but you are not going to get any insight into that solution. Therefore, we move into a territory of approximate dynamics, and we will appeal to the principle which we derived in the last slide, that is unbalanced force is equals to the total inertia force on the machine, and unbalanced moment is equals to total inertia torque on the moving parts of the machine. And with this we are going to get to a point where we have a very simple formula for the unbalanced forces and unbalanced torques that are hitting our engine. So, the approximate kinematics we will recall, just this was just the same as in the case of kinematics. In the case of kinematics, we firstly had an expression of for the exact kinematics, and then using the binomial series and truncating the binomial series, we obtained very simple expressions for position, velocity, acceleration, and that showed that the position, velocity, acceleration contains only two terms, namely contains only two harmonics in omega and 2 omega. So, we want something of that sort. So, we want similar multi-harmonic expression, and that is very desirable for the unbalanced forces and moments, because most of the times in vibration the frequency of vibration is very important from the design perspective. So, if you know the harmonics and if you know the amplitudes associated with the harmonics, it will be of great help in designing appropriate mounts, for example. Okay, so at this point we again take a note of the following fact on the kinematics of our engine mechanism. The kinematics is the following: the crank has pure rotation, the slider has pure translation. This part was easy, but it is the connecting rod which has a combination of both translation and rotation. So, that is what is referred to as complex motion. It is not to say that it is very complicated or something like that. It is just one notch a little more difficult to visualize probably than the crank or the slider. The crank motion is easy to visualize, it is undergoing pure rotation about the crank pin. Similarly, the slider is easy to visualize, it is only reciprocating within the inner walls of the cylinder, whereas it is the connecting rod which will undergo both rotation as well as translation. So, that is little complicated to visualize. So, it is in fact this connecting rod kinematics which is actually making it things very difficult for the exact analysis. So, what we try to do here is we will try to approximate the connecting rod in a nice fashion such that we are able to get around this difficulty. We will see how. So, since the connecting rod has complex motion, it is very difficult to establish what is the inertia force associated with this complex motion, which is a superposition of translation and rotation. Through a computer it is possible to determine, but again as I said that it is very difficult to get a formula out at this stage. So, the inertia forces will require us to find, let us say, the acceleration of the center of mass of the connecting rod. Unfortunately, that formula is not a very compact formula, is not a very simple to represent formula. So, this is where the difficulty lies in the exact dynamics, that the complication lies in the kinematics of the connecting rod, which does not permit us to find how the center of acceleration of the center of mass is behaving with time. So, that is what we will try and mitigate in a simplified analysis. So, therefore, the connecting rod now has been identified as the main culprit which prohibits our insight into the solution. So, we will try and attain a simplified model of this connecting rod and try to get around this difficulty where we do not know exactly how the acceleration of the center, or rather we know exactly how the acceleration of the center of mass is going to change with time, but that is not representable by a simple formula. It can be solved through a computer program, but what we are looking for is a simple formula based calculation which will in fact enable us to design better mounts, taking into account what are the issues associated with these unbalanced forces. So, with that in mind, let us move to dynamically equivalent model. So, we are considering this is a representation of what looks like a reasonably correct geometric figure of a connecting rod. This is how a connecting rod actually looks like. Now, I want to forget all the details and I want to say that I wish to have a simplified connecting rod. And what is my simplified connecting rod? Simplified connecting rod looks like a dumbbell wherein there are masses attached only at its end. So, just like in case you are doing weight training, you would see that in your weightlifting you would have the masses only attached at the ends of the rod. In comparison to the masses attached to the end of the rod itself is massless. It is not that the mass has gone 0. If you take a beam balance and measure the mass, definitely there is some mass. But in comparison to the masses carried by the ends, the rod appears very negligible mass. So therefore, we like at this stage to make a simplified model of the connecting rod, which is as follows. We want the masses to be concentrated only at the ends of the connecting rod, and the rod itself we want to make it massless. There is an advantage why we want to do so, that will be cleared in a moment's time. But at this stage, please bear with me in understanding that this is the objective that we have in mind, that the actual connecting rod needs to be replaced by a massless rod, and the masses with only lumped masses at both ends of this massless rod. So, this is a simplified representation which is comprising of a massless rod with two lumped masses at this center. We want this rod to be dynamically equivalent to the actual connecting rod. When can that happen? Two systems are said to be dynamically equivalent if three conditions are satisfied, namely mass is identical. So, whatever is the, if I take a weighing machine and find out the mass of this system, it should be exactly same as the mass of this system. So, mass between these two systems, the actual connecting rod and the connecting rod which is assumed to be massless but with end masses connected in a lump fashion as shown in this figure. So, mass has to be identical, that is the first condition. The second condition, that the center of mass should be at the same position. So, the blue dot in this figure, if you can see, is the center of mass of the actual connecting rod. The simplified system is dynamically equivalent if and only if, IFF is not a spelling mistake, IFF means if and only if. So, therefore, center of mass of the actual connecting rod should be exactly at the same location at the center of mass of the simplified connecting rod. And similarly, the moment of inertia about the center of mass of both these systems should be exactly the same. So, these three are the conditions which will enable us to say that the actual connecting rod is dynamically equivalent to this simplified connecting rod representation. So, the objective will be to formulate a dynamically equivalent model of the connecting rod, because we know that connecting rod is what makes the kinematics complicated. We want to mitigate that problem. So, we will formulate a dynamically equivalent model of the connecting rod as a massless link with lumped masses attached at its end. So, this is our objective, and with that in mind, let us see what is the condition that we are getting. So, the condition is as follows. So, we want the mass to be constant, that means whatever is the mass of our connecting rod, which was M3 as per the symbols that has been used in the earlier slide. So, this M3 has got to be equal to N1 plus N2, N1 plus N2 has got to be M3. Similarly, since the center of mass has got to be in the same position, so if this point has to be the center of mass, we must have N1 times A1 is equals to N2 times A2. N1 times A1 has got to be equal to N2 times A2 as per this criteria, that the location of the center of mass should be unchanged between the actual connecting rod and the simplified connecting rod. And lastly, the moment of inertia should be same. So, if the moment of inertia of the connecting rod is I3, the moment of inertia of the simplified connecting rod about the same center of mass has got to be N1 square plus A1 times A1 square, that is the moment of inertia of this mass, plus N2 times A2 square should be equals to I3. So, the moment of inertia of this system is N1 times A1 square plus N2 times A2 square, that must be equals to I3. So, we have to find A1, A2, M1, M2 such that all these three conditions are satisfied. But then A1, A2 is already known, because we want to find the ends of the connecting rod has to be exactly the same. So, because we want the connecting rod length to be the same as the simplified connecting rod, if we hold the lengths to be same, then the lumping will happen exactly at the big end and the small end of the connecting rod. actual connecting rod and the simplified connecting rod, if they have to bear the same length, then A1 A2 will also get fixed. So basically the only thing that you have at hand to choose is N1 and N2, but then there is no way in which you can satisfy three of these conditions by mere choice of N1 and A2, because A1 and A2 is given. Once you say that I want simplified connecting rod which is as long as the actual connecting rod, A1 and A2 gets fixed, right, because the center of mass is also the same. So this is A1 and this is A2. The only thing that remains to be found out is N1 and N2, and here you have three conditions to be satisfied. So you want N1 and N2 such that three conditions have got to be satisfied. So here you get to see a condition where you have two unknowns, but you have three equations to satisfy. All of them are linear in N1 N2, that is okay, but there is no way in which you will be able to satisfy all the three conditions using just two variables N1 and N2. A simple matrix algebra proof will demonstrate that this is not possible. So therefore, at this stage again we have to invoke some assumptions. So we satisfy the first two constraints exactly, that is the mass we hold is constant, the center of mass we hold is at same location as the actual connecting rod, but we ignore the last constraint on moment of inertia. So this may feel somewhat arbitrary at this point, but it is found out, it is known, it is given in the literature that when we take this lambda, and what is lambda? That is crank radius by connecting rod length. When crank radius by connecting rod length or connecting rod is large compared to crank radius, this discrepancy is actually small. A more involved analysis will tell you this, and this analysis also will tell you that if you are very bothered about this discrepancy in moment of inertia, it can be corrected by the application of inertia torque. I will recommend that you read the textbook, which is Ghosh and Mallik's book on theory of machines and mechanism. That book has the proof that why we leave out this moment of inertia. I am just making a statement that if lambda is small, leaving out moment of inertia does not imply much of error. The discrepancy in moment of inertia is actually minimal, and even if you think that it is not up to your satisfaction to leave that moment of inertia term, then it can, this arbitrary step that we are taking can be sort of corrected by applying an extra inertia torque, which is exactly what is given in the book, but for the want of time I do not want to dwell in that direction. In case you are interested, please read the book, it is given in that in Ghosh and Mallik's book. But at this stage I will say that therefore if I can choose N1 and N2 such that N1 plus N2 is equals to M3 and N1 A1 equals to N2 A2, I would have attained my objective in constructing an equivalent connecting rod. A connecting rod which has same mass, which has same center of mass, but definitely has a different moment of inertia. But this moment of inertia is possibly not going to get, this difference in moment of inertia is possibly not going to be much, provided the lambda that I am interested in is small. If lambda is small, then this discrepancy in moment of inertia has been found through calculations to be minimal, and in any case this can be corrected. It is not that it cannot be corrected, it will just allow if you just include one more torque and another inertia torque which is basically arising due to the discrepancy in this moment of inertia, then we should be able to correct this step later also if we want. So with that assumption we will be now satisfied with our dynamically equivalent model, but then the question arises, how does this simplified dynamically equivalent model actually help us to find the unbalanced forces? So that is what we are going to do in the next slide. So in the next slide, if you now see, the purple color is as usual our crank. So the purple colored link is the crank, the red colored link is the connecting rod. But this time we are taking a simplified representation of the connecting rod, which means the red line is actually massless. The entire mass is apportioned at the big end and at the small end. So at the big end, for example, you have this mass N1 sitting, and at the small end you have the mass N2 sitting. So this crank is actually, this connecting rod is massless. The lump the lumped mass associated with the big end of the connecting rod is shown here. The lumped mass associated with the small end of the simplified connecting rod is shown here in red, right. So the way this simplified model now helps us is that in the following. So the crank, remember the main issue was that we were unable to sort of visualize what is the inertia forces and inertia torques arising due to the connecting rod motion. The crank and pistons were easy. The crank, let us say it has a center of mass as is indicated by this black dot. So as the crank is rotating, there will be m omega square r, which is m omega square d2, I am sorry, m2 omega square d2 is the inertia force associated with the crank rotation, right. That was easy, but the connecting rod created a problem. But now how have we solved our situation? Instead of taking the connecting rod, we are taking two masses n1 and n2, but n2 is rotating at exactly the crank radius and n1 is rotating exactly the crank radius, and n2 is along with m4 undergoing only a reciprocating motions. So therefore we have resolved the complex kinematics of the connecting rod into two simplified kinematics of the mass n1, which is rotatory, and the mass n2, which is reciprocating. So the mass n1 is rotating and mass n2 is reciprocating. Now it is very easy to balance the masses m2 and n1. Now you will note that with rotary balancing we have already accomplished this, that if there are two unbalances along the same line, one at D2 and one at R, then you can mitigate this unbalance by simply keeping a counter mass MB in the other direction, such that MB times E2 should be equals to M2 times D2 plus N1 times L2. This distance is L2. Okay. So N1 times L2 is the unbalance due to this blue mass, M2 is times D2 is the rotary unbalance due to this black mass. This has to be balanced by putting a counter mass on the other side. So MB times E2, if you put the counter balance exactly in the opposite direction, you should be able to balance this system. So that is why exactly you will see that in the crankshaft construction you will have webs in one direction. So these webs are supposed to be the counterbalances which balance the crank mass together with the apportioned mass of the connecting rod which is sitting on the crank pin. So at this stage with this counter mass, what have we achieved? We have achieved our objective that there are no rotary unbalances that is left in the problem. The crank was having rotating unbalance, the connecting rod which was simplified to two lumped masses, one was having rotational motion and the other was having reciprocating motion. The fact that one was having rotational motion at the crank pin was very useful in deciding a solution, in deciding a mitigation procedure, as I was referring to a few moments back. I am now able to balance at least the rotating parts of this machine very easily, because there is only one rotating part associated with the crank and there is only one rotating part associated with the connecting rod. The connecting rod rotary mass is sitting exactly at the crank pin. The crank mass which is rotating can be lumped exactly at its own center of mass. So therefore now you have the center of mass of this system to be exactly at the hinge point. So therefore there is no unbalance left in terms of the rotating masses of your IC engine. Remember, in the IC engine there are rotating component like crank, there is also a reciprocating component. So the unbalance due to rotary components at this stage has been killed. There is the unbalance due to reciprocating mass which still remains. So the reciprocating mass N2 and M4. Now not only the M4 which is the slider mass reciprocates, but also the mass N2 which is the apportioned mass coming from the crank to coming from the connecting rod to the piston, that apportioned mass is also reciprocating. So together they will have a reciprocating motion. N2 will have identical motion as the piston. So M4 x double dot is the inertia force of the piston. Similarly, N4 x double dot with a minus sign is the inertia force of the apportioned mass coming from the crank connecting rod to the piston. So therefore, what is the total inertia force? Total inertia force is minus M4 x4 double dot plus minus M4 x double dot minus N2 x double dot, or in other words the total reciprocating mass is M4 plus N2 and the acceleration of both these reciprocating masses is x double dot. So therefore the total reciprocating mass times the acceleration of this reciprocating mass with the negative sign is the total inertia force, and we have already seen the total inertia force is equal to the total shaking force that the frame feels. But now please appreciate the power of this simplified analysis. You are seeing that there is only one inertia force that is there in this system, because after this counterbalance has been used, the rotating masses have all been balanced. There is only the reciprocating mass which even at this stage is not balanced. They will involve the inertia term. So therefore the total inertia term is mREC times x double dot. mREC is precisely M4 plus N2. mREC is the mass of the entire reciprocating parts. The entire reciprocating parts is not just the slider mass, but also the apportioned mass of the connecting rod which is sitting on top of the slider mass. And we have already found out in yesterday's in the last class that there is a simple expression for x double dot which is minus omega square r cos omega t plus lambda cos omega t. So therefore we are now seeing a very simple expression which I can write in one line, that is what is the shaking force on the frame of an IC engine. This is exactly mREC. mREC is the mass of the reciprocating part. mREC times r times omega square. What is r? R is the crank radius, cos omega t plus lambda times cos 2 omega t. This was exactly my objective, that to give you a very simple formula for the shaking force. Also what I have attained is that there is no shaking force in any other direction other than x, because the only mass which is having some motion left is the reciprocating mass. The rotary masses are completely balanced at this stage. So therefore there is only reciprocation in the x direction, that leaves us with inertia forces only in the x direction. There is no moment, there is no inertia force in the y direction, there is only inertia force left in the x direction, which means you are going to get only a shaking force in the x direction. Shaking moment is 0. So at this stage we will try and interpret this shaking force in another way, that is we are seeing that it has a cos omega t component, it has a cos 2 omega t component, which means you will note that this is like rotary, this term you will recall is like a rotary unbalanced term. M omega square r is the force that is created due to rotating unbalance, but this time you are multiplying this over cos omega t and cos 2 omega t with the lambda term. So that means the total shaking force is along the x component of these rotating vectors. So if I have mREC r as the unbalance and mREC r times lambda as another unbalanced force, each of them are rotating at omega and 2 omega, the component of these rotary unbalances along the x direction is exactly my shaking force, and that is going to give me great benefit in designing ways and means in which I can reduce the shaking force. At this stage I will again take a pause to let you ask me some questions, and I will come back to this portion in a few minutes time. But by this time what I want you to appreciate is that how the exact analysis was done, how the approximate analysis was done. The approximate analysis definitely is not completely accurate, but with the assumptions that were inbuilt in the approximate analysis, we were able to get a very nice and compact expression of the shaking force along x direction, and shaking moment was completely 0, shaking force along the y direction was completely 0. After the interactions in for a few minutes, we will come back and again reflect and how to use this formula in order to get a better design in terms of balancing of our reciprocating machine. I will take a few questions at this time. DSRU is asking me capital M will be applied on the crank from where? Capital M, which is the if I have to look back at my slides. So capital M is the moment that is applied on the crank. Obviously capital M is not applied by the connecting rod on the crank, because there is no such connections which permits application of the moment from the connecting rod to the crank. The connection between crank to the connecting rod is through this revolute pair. Through a revolute pair you can only transmit forces, you cannot transmit any torque. The other part which connects to the crank is the frame. So obviously if there is no way in which from the this moment can come from the connecting rod, it comes from the frame. So therefore capital M is the moment which is applied to the crank. Whatever is applied to the crank has to come from the frame, and therefore the shaking moment which I just talked, or the reaction to this will also come to the frame. So in this slide you will recall I have given a picture where equal and opposite moment comes to the frame. So this implies the frame gives this moment M. By frame what I mean is anything which is connected to the frame is going to, anything which is external to the moving parts is the frame. So anything which is external to the moving part is equivalent to that load torque, and therefore a reaction to that moment is coming on your frame also. I hope that clarifies the question. Next we will move on to PECTN's question. Is there any center of gravity to be considered for the piston? I hope I have made myself clear that for the piston is the center of mass. I really do not understand what you mean by center of gravity, but in this case we are concerned about center of mass. In the piston case, all the forces are passing through the center of mass, and therefore there is no issue of moment. So A4 and A3, this piston is only having a sliding motion, so therefore all points have identical motion. So whatever is the motion of any arbitrary point is the motion of the center of mass. So you really do not need to worry about where the center of mass is, as long as you know that the line of action of all these four forces passes through the center of mass. If the line of action of forces is not aligned, then you will have some rocking motion, piston slap and whatnot, those are complicating features. But at this point we are assuming that all these forces are passing through the center of mass, and hence the piston is having only a reciprocating motion. So once a body has a translatoring motion, then all points in the body has identical motion. I do not need to worry where the center of mass is. The center of mass acceleration is same as the acceleration of any other point. So therefore this is the question of center of mass for the piston is irrelevant, hopefully with the understanding that all the forces are passing through the center of mass. Okay, another question. CEC Gurikrat is asking me why shaking moment is 0. Shaking moment is 0 as is borne out from the simplified analysis. In the simplified analysis that has been presented here, you will get to see that there are no inertia torques in this simplified model. In the simplified model, the rotary parts are completely balanced. There is only one inertia force. There is only one mass which is having any kinds of inertia force, that is associated with the reciprocating motion. So therefore, as our analysis tells us that the inertia force is the shaking force and the inertia torque is the shaking torque. Here in the simplified analysis, it is very easy to see that since there are no inertia torques in the system, so therefore there is no shaking torques. Okay, so that is done. PSGC gas force transmitted to connecting rod, we'll talk
on the frame too, sir. Sir, you have considered the gas force on the frame.
Yes.
But if we consider the gas force is totally transmitted to the connecting rod, we should not consider it on.
No, I'll tell you why. I'll tell you why. So if you can see my tablet, this is the cylinder casing, this is the piston, this is where the gas force is living. So this is the piston. So the gas force, this is the frame, this is the crankcase. So this is the crankcase, this is the piston. So therefore now let us look what is happening. So it is in this chamber. So this is the combustion chamber where the combustion is happening. So this is EA which is hitting the piston, but then on the other side this gas force is also hitting the crankcase. So therefore the crankcase is also getting the gas force, just like the piston is getting. Okay.
Yes,
So therefore the crankcase is the frame that is not moving, right, and this is the piston. This piston is getting the gas force. So now if I look back at my presentation material, so this is the force which is hitting the piston, and this force is basically this force. This force is what has been indicated in the frame. Okay.
Okay, sir. Thank you. Yeah, thank you, sir.
So at this stage, as we have seen, we have been able to find a nice compact representation for the shaking force, which is this. Now it is, and shaking moment is 0. Now this shaking force can also be thought of as a rotating unbalance, but the force in the rotating unbalance goes in all the direction, but here it is only the cosine component of this rotating unbalance which will hit our frame. So mr square omega is the magnitude of a rotating unbalance, with the value of unbalance being mrec times r, but rotating at the speed omega. So to understand what this shaking force is, I can as well think that this is a shaking force due to a rotating unbalance of magnitude mrec r and rotating at a speed omega. But unlike a rotating unbalance wherein we try to wherein we know that the forces induced due to rotating balance will have components both in y direction as well as in x direction, this time we have to take into account that it is only the x component of this rotating unbalanced force which is the shaking force. So the shaking force is now construed as the x component of the rotating unbalanced force. Similarly, mrec r times lambda can be construed as a rotating unbalance with rotating at 2 omega. So this time there has to be a by 4 factor, because when you put 2 omega whole square you get a 4. So that is a rotating unbalance with 4. So the x component fx is the x component of unbalanced force due to rotating unbalance with mrec r rotating at omega and mrec r lambda by 4 rotating at 2 omega. So I have missed out that by 4 factor in the slide. Please make that correction. I will myself do it in another revision which I will upload at the end of the course. So either you can say that the primary force mrec r omega square cos omega t is a rotating unbalance in the x direction, the magnitude of unbalance being mrec r, and it is rotating at the speed of omega. Similarly, the secondary unbalance, which is mrec r times lambda, but it is rotating at 2 omega. So instead of having, I'll write this for you once because I have made a mistake. So the actual unbalance is mrec r times lambda times omega square cos of 2 omega t. So this I can write it as mrec r lambda by 4 2 omega whole square cos of 2 omega t. So this effectively means a rotating unbalance of mrec r times lambda by 4 rotating at 2 omega. So however, just the so this part means a rotating unbalance, but then you have to take only the cosine component of it, which means you have to take only the x component of this rotating force. So that's what I meant, that you can now, instead of thinking of shaking forces in reciprocating terms, you can think of this as shaking forces in terms of rotary machines. So these shaking forces which are induced are equivalent to the shaking forces which would have been induced due to rotating unbalance of mrec r rotating at omega and mrec r lambda by 4 rotating at 2 omega. Again, apologies, I have missed out that factor by 4 in the slide over here. Okay, so carrying on, therefore what we have got at this stage is this, that this entire simplified representation of the IC engine mechanism is equivalent to two rotating unbalances, one which is MREC R which is rotating at omega, and the other which is MREC R lambda by 4. Again I have missed out the factor by 4, MREC R lambda by 4 which is rotating at 2 omega. So these are the essentially two unbalances that are present in my system, and this is what is hitting my frame. So in order to save this, what can I do? So now coming to how we can balance the slider crank mechanism. We can balance the slider crank mechanism in this fashion, and this is why the approximate analysis is so very interesting, because it leads us to the procedure of balancing. The exact analysis, though everything is correct about it, it did not lead us to the procedure of balancing. So at present we are able to realize that these forces which are acting on the frame are nothing but rotating unbalances MREC R and MREC R into lambda by 4, which is rotating at omega and 2 omega respectively. Wherever you see lambda, it is supposed to be lambda by 4. Again, sorry for that correction, for that mistake. I will make the correction in a revised notes which I will upload. Fy is 0, so no issues associated with that. So the shaking moments are also gone to completely 0, so there is no issue about shaking moments also. So the question is, how do we balance this force? So for balancing the primary, which is associated with cos omega t type of term, so the cos omega t term can be very easily balanced if we realize that it is a rotating unbalance. So if it is a rotating unbalance which is MREC R, then if we add a counterbalance to it which is of the same magnitude MREC R, we should be able to balance this situation. So if we add a counter mass which is MREC R in the opposite direction of the primary unbalance, which is oriented along the opposite direction of the primary unbalance, then we will be able to completely balance this situation. So let me get back to my notes and tell you how this will be done. So as I said that the primary force, the primary unbalanced force that you see is because of is made equivalent. So this is my x direction, which is the direction of slider motion. So what we have shown to you is that the primary unbalanced force is equivalent to the x component of this rotating unbalance. What is the value of it? The value of it is MREC R. So this situation could have been simply saved by putting another counter mass which is MBRB, such that MBRB is equals to MREC R. So this will enable you to get rid of the x component of this unbalanced force if you want. But then there is a problem. In the actual picture shown here, there is no y component of unbalanced force. But once you introduce a counter mass, you will be introducing unbalanced force even in the y direction. So there will be a y directional, so addition of counterbalance will induce y directional forces, which you do not want. In the original system, without the addition of your counter masses, there were no y directional shaking forces, there were only x directional shaking forces. You realize that those x directional shaking forces are equivalent to the x component of the rotating unbalances with magnitude MREC times R. So therefore you thought that by putting a counter mass you should be able to resolve the situation, but then though you have killed the problem in the x direction, you have made a new problem by putting it in the putting a counter mass in this fashion. Similarly, for the secondary, what happens is the following. For the secondary, you have a mass which is MREC times R times lambda by 4, which is rotating at 2 omega, and you should consider only the x component of it. Okay, only the x component of this rotating unbalance is actually hitting the frame. The y component has no relevance. You could balance this situation by putting a counter mass in this fashion, such that, and I'll call this MSES. So MSES, if you choose this to be MREC R times lambda by 4, then obviously the x component of the secondary also will get nullified, but once this 2 starts rotating in 2 omega speed, it will generate a y component of the force, right. So if you use counter masses without applying this logic, then you will be able to resolve the forces or nullify the forces along x direction, but you will create new forces in the perpendicular direction. So actually what is done in industrial application is that you will not do any of these. So therefore for balancing the primary, what is to be done is we put an unbalanced rotating force mass which is MREC R, which is opposite to the primary unbalance, and therefore the primary unbalance you know is oriented along the crank. So just opposite to the direction of the crank you put the counter mass, that will help you get rid of Fx. But then the addition of this unbalanced rotating mass will induce shaking force in the y direction, which is definitely not desirable. So therefore in practice what will be done is only a fraction of the unbalanced force in the x direction will be mitigated. That will lead to a fractional quantity of unbalanced force coming in the y direction, but we will not try to completely balance the x directional forces, because if we try to completely balance the x directional forces, the y directional forces will completely take on its effect. Rather we will take a 50% let us say reduction in x directional forces. As a result 50% y directional forces will also be generated, but that is sort of a trade off. That this method is not going to give you a complete balance by putting counter masses. Complete balance can be achieved through Lanchester balancing technique, and Lanchester balancing technique is shown here in this diagram. The idea is very simple, that instead of putting one counter mass you put two counter masses. So we have here two discs shown in dotted lines, both of these are rotating at the opposite speed, and these counter masses are MP, EP. I am showing the Lanchester balancing only for primary, secondary is similar, so I am not showing it. So we are adding two unbalanced masses rotating in opposite direction. This unbalanced mass is going to create the unbalanced force in this direction. Similarly this rotation is going to create unbalance in this direction. These two unbalanced masses is going to add up along the x direction, which is the direction of slider motion, but these two unbalanced masses will in fact nullify each other in terms of the y directional forces. In the earlier philosophy the problem was the addition of the unbalanced masses, rotating masses, was creating y directional forces. So here I am not adding a single mass, I am rather adding two counter masses, each of them rotating in an equal and opposite fashion as the primary. Now what is happening is that both of these counter masses are adding up the forces along the direction of slider motion, but they are nullifying each other with the perpendicular direction. So the addition of one counter mass did not work, but the addition of two counter masses, which is MP EP equals to MREC R by 2, that will work in order to save the day for us, and now we will completely kill the primary excitation forces which are coming in the system. Similarly it can be, so Fy is cancelling between these two rotation, Fx is actually adding up between these two rotation, and this Fx is now cancelling the Fx produced by the crank. So we know that the reciprocating force is equivalent to the rotating force along the x direction. So we had to do something to balance this rotating force along x direction, and this is what we do. We put in two unbalances, these two unbalances are mutually cancelling each other along y direction, and along x direction they are exactly equal and opposite to the reciprocating unbalance which is there in the piston. So with this we have attained primary balancing of our system. Secondary balancing also can be done for the other order. There we have to have just a similar arrangement, but rotating at 2 omega speed, and there we have to take the counter mass, which is mREC times R times lambda by 8. Just like here MPEP was mREC R by 2, there we will have mREC R lambda by 4 by 2, which is lambda by 8. So that with that correction we can have a Lanchester balancing where each and every order can be balanced, but however you will rarely see an engine where Lanchester balancing is done. That is mainly because of the fact that you will not have enough space in your automotive engine compartment to put these two big discs, so or other discs also. So sometimes dictated by space constraints, this Lanchester balancing will not be done, but I wanted to show you at least an academic example where if you want you could completely kill all the unbalanced forces if you want, but sometimes due to reasons which are beyond technical, we are not able to implement these solutions in practice. Okay, I think before moving on to multi-cylinder engine, let me again pause for a while. We have finished our analysis of single cylinder engine, and if you wish to have some interactions we can have, in which case I can leave out multi-cylinder engines, but if there is about 5 minutes time left after interactions, I will again come back to multi-cylinder engines and complete my talk on that. Please feel free to interact with me on single cylinder engines if you want to. Any questions on this portion of the material? Okay, DCRU asking me is how can we write x double dot in the form of lambda and omega. So that was what was done yesterday. If you recall, we had obtained the approximate expressions for acceleration in yesterday's class. This is what x double dot by omega, I mean the acceleration of the piston in terms of the angular velocity of the crank. So this is exactly what we have referred to. Okay. So in slide number 31 you will get to see how the acceleration of the piston is related to the crank speed. Fine. If there are no other questions, let me continue with multi-cylinder engines. So unlike in Lanchester balancing, what will be done in industrial applications is typically shown in multi-cylinder engines. So in multi-cylinder engines you have a number of engine slider crank mechanisms which are mounted on the crankshaft. So the black is the actual shaft, and each cylinder is having a web. Each of these IC engines will have this crankshaft which is shown in red, blue and green colors, and they are all getting connected to a common crankshaft, right. So the firing order of these engines are different. So we have taken for illustration a 2-stroke engine, but it is 4-cylinder and inline, which means a 2-stroke engine completes its cycle in 2 pi. So with one rotation of the complete crankshaft, the entire engine cycle is completed. And now if you want to fit 4 cylinders within that cycle, that means each of those cylinders will have a phase gap, a delay between themselves of 90 degree. So what is shown here is firing order 1, 2, 4, 3, which means first the cylinder 1 fires. Let us say the firing happens when it is at the top dead center. So in this position 1 is at the top dead center. When it rotates a further pi by 2 angle, then it is the cylinder 2 which will fire. Then when it rotates further, it will be 4 and then it will be 3. So 1, 2, 3, 4, that is along the axial direction, whereas the firing order would be first 1, then 2, then 4, then 3. That depends upon the orientations of the individual crankshafts, right. So here you have the cranks oriented, the orientation between these cranks is at a phase delay of 90 degree, but now because there is a firing order that is present in the system, not all of these cranks will fire simultaneously. When the 1 is fired, 2 is not getting fired, 3 is not getting fired, 4 is not getting fired. Every crank will get fired only when it is at the top dead center, which is this position, right. So therefore in this configuration 1 is getting fired, 2 will get fired after a 90 degree rotation, 4 will get fired after a 180 degree rotation, 3 will get fired after a 270 degree rotation. So this is the configuration of the system. Now we know exactly, and in side view if I look at it, this same diagram will look like this, which is not very important. What is very important is to understand that the forces which are transmitted to the frame is along the direction of slider motion, right. So we have already said that we can replace the primary forces with an equivalent system which is rotating in alignment with the crank, but then we should take only the x component of it. So for example, this red crank will induce a primary force which is along the red direction. So the primary force induced, this is the vector which is showing the primary force. So the primary force induced because of the first crank is going to have the same direction as the direction of the first crank, the red crank. Similarly, the primary force that is induced by the green crank will be completely in the opposite direction. For the second crank, which is shown in magenta here, again it is aligned in this fashion, but please remember that we are only going to take the x component of it. So whereas this and this are the real forces, these are sort of imaginary forces and they are needless to worry at this point. But even then, even for the sake of completion, if we wish to draw all the forces, so as I said, the way to determine these shaking forces is to first consider the rotating unbalances and then take the x component of it. So at this stage we are not worried about taking the x component of it. We will just find the total rotating unbalance due to this group of force. We know that finally the total force has to be resolved along the x direction, which is the direction of the slider motion. The slider motion for all these four sliders is got to be the same, which is denoted as x. So at this stage we are just taking the sum total of the rotary unbalances associated with each of the crank without worrying about taking the components. So as we know, the crank directions will point out to the direction of unbalance. So this is the direction of unbalance associated with the first crank. This is the direction of unbalance associated with the fourth crank. This is the direction of unbalance associated with the second crank, and the direction of unbalance associated with the third crank is from right to left. So here we see, since each of these unbalances are having a value MREC times R, and MREC, and since all these engines are identical, all the slider cranks are identical, MREC times R is identical for all these cranks. So therefore this forms a closed figure. And if I don't take x component, the sum total of the rotating unbalances in this case is 0. So therefore if the sum total is 0, the x component of the rotating unbalance is also 0. So therefore in this fashion I have completely killed the primary unbalanced forces, right. The secondary unbalanced force is even simpler to analyze. In the secondary, this is the primary crank diagram. In the secondary, since you have a 2 theta sitting in your trigonometric terms, so therefore the angle between 1 and 2 in the secondary will not be 90 degree but double of that. So therefore the angle will be 180 degree. Similarly, the angle between 1 and 3 won't be 90 degree, it will be 180 degree. And lastly, the angle between 1 and 4 won't be 180 degree but it will be 360 degree. So 1 and 4 will now get completely aligned and 2 and 3 will now get completely aligned. Again, since all of these forces are equal in magnitude, but you see the red is getting cancelled by the magenta, the green is getting cancelled by the blue, and therefore you are getting a secondary force also getting cancelled. So here we have brought out a situation where naturally you do not have to invoke Lanchester balancing. Naturally, because of the nature of the symmetry of all these four cranks, naturally everything is getting killed, both the primary, the secondary are getting killed. You do not have to worry anything in terms of balancing these engine forces, and that is why Lanchester balancing you will not see in practice, because this is automatically taken care in multi-cylinder inline engines. Just in the next 1 minute that we have, we can take a quick look at the moments also. So just like we did the moment diagram for the rotating unbalance, we can do the moment diagram for this case also, with the understanding that we have resolved the system into a system of rotating unbalances. So associated, so for doing so we take the reference plane right at the center of our engine. So we have already known the convention that the moments associated to the right of the reference plane is supposed to be having the same direction as the orientation of the unbalance, that is the rotated moment convention. So the green moment is same as in direction as the orientation of the unbalance, whereas the red moment is opposite to the direction of the unbalance. And please note that the moment induced by the red and green is going to be higher than the moment induced by the blue and the magenta, because the moment arm corresponding to the blue and magenta crank is going to be much lesser than the moment induced by the red and the green crank, because they are further apart from the reference plane. So the green and red are going to be larger in length, the magenta and the blue are going to be smaller in length. So therefore this is the total moment that is acting, and then therefore the total moment is shown in this black dotted line. But here again we must remember that it is only the x component which matters. So if you have to know what is the instantaneous moment that is hitting at this instant, therefore you have to take only the x component of this dotted arrow which falls along this direction. At a later instant, this drawing is shown in this fashion, the system has rotated by pi by 2. So again at a later instant you will see that the moment diagram has got itself rotated in this fashion, and again the dotted arrow represents the total rotating moment, but then we must take the x component of it, which means the total rotating moment at the total moment hitting our frame is actually this much. But then there will be some intermediate configuration wherein the total moment, this dotted arrow, will exactly align itself in the x direction. So therefore this moment is in fact going to be the maximum moment that you will get in your frame. So therefore though we are able to resolve the primary forces and the secondary forces, the moments associated with the cranks are still remaining, and this is how we can calculate the maximum moment which is hitting the frame of our or the crankcase of our IC engine. And I think at this stage I will conclude my talk here. I will in the next 2 odd minutes that is remaining, and even afterwards if you wish you can interact with me. The last part had been little fast to my satisfaction, but I hope you get this idea that the build up from the rotating unbalance is very important to understand the reciprocating unbalance, and it is very important to appreciate the role of approximate models in our understanding of how unbalanced forces can be mitigated, how in a multi-cylinder inline arrangement the unbalanced forces are actually getting killed or nullified, how there are moments that are left in the multi-cylinder configuration is going to be induced in the crankcase. So with this I would like to end my talk here. If there are questions or interactions you guys want to have, I will be happy to take it. CTU is your, yeah, please pose your question with.
Sir, I want to clarify the total reaction pair which you have taken in piston cylinder arrangement. R1, 2, R3, 4, all the reaction pairs.
Okay, so if you can see my slides, you can see my slides, right? Okay, I'll bring that up for you in a moment. Okay, is this the slide that you're talking about? Slide number 34?
Yes, sir.
Okay,
Yes, sir.
R12 is the force that is coming from 1 to 2. That 1 is our frame, 2 is our crank. So R12 implies the force from 1 to 2. Fine. So there is the interaction force between 1 and 2. Similarly, 1 4 is from 1 to 4, 3 4 is from 3 to 4. Okay.
Yes, sir.
Does that clarify?
Yes, sir.
PSGCT, you can do the analysis that you have recommended. That analysis will give the same result as I have shown you. You are saying that consider the inertia force of the slider. In fact, I have considered only the inertia force of the slider. Everything else will just get cancelled. I know the analysis that you are referring to is given in some books, but you will appreciate that analysis will give exactly the same result as I am presented to you. So your suggestion is inertial force of the slider is moving in case it is completely gas force on the slider is a known force. It is not going to change with the it does not depend upon the motion of the slider. It depends upon the crank angle. So PSGCT, you are asking me that why haven't we considered inertia force of the slider? My counterpoint to you is that we have considered only the inertial force of the slider, nothing else is considered. Okay, so M REC times R is the reciprocating M REC times R into omega square is exactly arising because of the inertia force of the slider. Okay, the gas forces rather are not considered, because if you do it in terms of gas force, it will get a little clumsy, but then you can show that the gas forces actually don't bother. Gas forces will actually get killed, it does not matter. Okay, I think I'll move on to the next question. How are radial engines balanced? This talk is about inline engines. I have actually done little, to be very truthful, I think I have been very fast in the inline engines part. So I don't think it is appropriate to talk about any other configurations. So please, if you want, you can study it by yourself. I don't want to talk about configurations which are uh, other configurations of engines, but the idea is basically the same. In radial engines you will have lots of cranks, so these orientations will be 2 pi by n, and you have to do similar kind of analysis to do it. But I will appreciate if the students can take away from this talk how unbalanced forces arises in a single cylinder engine and how it can be carried over even to multi-cylinder inline configurations. As a homework, the students can think about radial engines also, but my talk, since it has far outshot the time, I have not discussed anything about V engines or radial engines, but you can take that as a homework. Okay, anything else? I hope you have practiced the problems that have been posted in the course pack. Some of them are pretty simple, some of them are not so simple. You will get to see the detailed questions where you require pen and paper calculations, possibly today in your course pack. We have already submitted them for uploading, and as I said, I will be giving a revised version of these slides which includes these corrections as I have mentioned. You are free to post your questions in the forums of the course pack. It should be active for the semester at least. I will definitely respond to your questions posted in the forum, and if there are any way in which I can help you with your learning, I'll be happy to do so. Before signing off, I just wish to clarify that there are excellent video lecture materials available in the NPTEL site and the YouTube site for free. And this part of the talk is mostly about Amitabh Ghosh's lectures on dynamics of machines available in NPTEL. Some part of the talk is also coinciding with Professor Mallik's talks on kinematics of mechanism. So I will strongly encourage you to look through these video lectures, and the book by Ghosh and Mallik, which are these people, is also very nice book on machines and mechanism, and this is slightly offbeat book, but I strongly suggest that you read this book to gain a good understanding of this subject matter. You will be able to access my slides in the course pack. Please feel free to do so, and as I said, if you have any doubts, post them in the forum. I will be able to answer. CIT CMB, you want to ask me a question? Please go ahead and do that.
Good evening, sir.
Good evening.
How to figure out the primary crank and secondary crank in multi-line engines?
The primary crank will be exactly the crank that you are seeing. Secondary crank is the crank which is at double the theta with respect to primary. So if your primary crank is making an angle theta with respect to the direction of your slider, then the secondary crank will make an angle 2 theta with respect to the direction of your slider motion. That's all. Primary crank is the crank which you are visibly seeing, right? You got primary crank? Did you get what is primary crank?
An angle 2 theta.
Sorry?
At an angle 2 theta, it will be the secondary crank.
Primary crank is at an angle theta. Primary crank is that which you are seeing visible in your construction, right? The crank that you are seeing is the primary crank. The secondary crank will be at a double the angle of it. Secondary crank is actually not visible. It is just a concoction. It's a man-made thing, it's an artificial thing. If the primary crank is at an angle of theta with respect to your x direction is the direction of slider motion, then secondary crank is at 2 theta, which is to be imagined. It is not there in the system.
Yes, sir.
Am I clear?
Thank you, sir.
Okay, good. Yes, you
Good
want to
evening,
ask
sir.
something? Yes, good evening.
Sir, you have talked about the firing order now, sir. You have said
Yes.
it is based on the orientation of the engine now, sir. Orientation means in which sense, sir?
No, orientation, I would have used it in this way. You can see my slides? Can you
Yes.
see my slides?
Yes,
Can you
sir.
see my slides? So by orientation, what I meant is that there are 4 cylinders and you have a 2-stroke engine, right? So 2-stroke engine means
sir.
the entire cycle has to complete in 1 revolution of the shaft, right? So if I
Yes,
have
sir.
to arrange 4 cylinders such that after 2 pi everything goes back to its normal, that means each of the crankshafts should have a angular orientation with respect to each other as 2 pi by 4, which is 90 degree. Are you with me on this?
Okay, sir. Yes,
Okay.
sir.
Then the next question comes as firing order. The next question of firing order is answered in this fashion, that as a convention we take this first cylinder to be firing first, which is always at the top dead center. Okay. Now if 2 is at this orientation, then the next cylinder to fire, once it moves, once the shaft rotates by omega, this 2 will come at the top, right? You can see this in this figure. So between these 2 instants, you see at this instant 1 is at the top, at the next instant or at the next time, which is pi by 2 omega, 2 is at the top dead center. So that means 2 is firing, right? In the next instant, which is not shown, 4 will fire. In the next instant, it is 3 will fire. So this is what I meant by saying the orientation of these cranks will determine the firing order. So
Okay.
if I have the orientation of the cranks in this fashion, 1, 2, 3 and 4 as you have seen here, that means first 1 will fire, then 2 will fire, 3 won't fire after this 2. It is 4 which will fire after 2, and then 3 will fire, and after 3 again 1 will fire. So depending upon the orientation,
Okay.
you get a clear idea as to which crank will occupy the top dead center position. Once the crank goes to the top dead center, firing will happen. Got it?
Okay, sir. Okay, thank you, sir. Yes, sir. Thank you, sir.
With that, let us call it a day. Thank you so much for your patience.